Okay, this VodCast that we're starting with this particular chapter is VodCast 10-1, and this is the start of moles. This particular chapter is more of a background chapter to help us in the future. What we're going to learn to do in this particular chapter is count atoms and do a lot of the basic math that we're going to need for the future. Okay, in this particular chapter, you must have a calculator. So if you do not have one, pause and get a calculator now. The basic premise of this particular chapter is what is referred to as Avogadro's number. You have heard this before. You should write this down, as this is the definition of Avogadro's number. It is the number of particles in 12 grams of carbon-12. So it's an exact amount. If I massed out 12 grams of carbon, okay, I would have Avogadro's number. This is what Avogadro's number is. Avogadro's number we also refer to as a mole. And 1 mole, which we will write as MOL, is equal to 6.022 times 10 to the 23rd. This is a number you have seen before. This particular number is the chemist's counting unit. Now, you can have a mole of just about anything. You can have a mole of Skittles, you can have a mole of M&Ms, you can have a mole of pencils. A mole is a counting unit, just like a dozen. And most people don't understand that, okay, I have a dozen, and everybody understands that 1 dozen is 12 of something. Well, 1 mole is 6.022 times 10 to the 23rd of something. Something else to keep in mind is that when we say Avogadro's number, that is Avogadro's number. Avogadro's number is also 1 mole. Those terms are synonymous terms. They're all interchangeable. Okay? Now, how big is a mole? Okay? These are some definitions just to give you kind of an idea of how big a mole really is. Okay, and I'm going to let you read them on your own. So if you need more time to read, go ahead and pause the VodCast. But do take a moment to read them. Now, this last one is actually one we're going to work out because I think it's kind of interesting. Let's say you won the lottery and you won Avogadro's number of dollars in that lottery. Okay, so you won 6.022 times 10 to the 23rd dollars. Okay, and basically what I'm asking you is, if you spent $1 billion an hour, that's right, $1 billion, and this is what a billion looks like, which is 1 times 10 to the 9th dollars. Okay, how long would it take to spend $1 billion an hour? Okay, well, this is just an interesting problem. So if you start this out, I have 6.022 times 10 to the 23rd dollars. Okay, and what you're going to do is you're going to spend, for every 1 hour, you're going to spend 1 times 10 to the 9th dollars. Okay, that's $1 billion. I just didn't really feel like writing out all those zeros. So that's $1 billion right there. Okay, there are 24, excuse me, for every 1 day, there are 24 hours. And for every 1 year, we'll just call it 365 days. Okay, so days would cancel, hours would cancel, the dollars would cancel, so that would leave me with years. Take a moment and plug those numbers into a calculator just so you can remember how to do these conversions. This whole particular chapter is going to be about doing conversions. And if you get this, you get 6.87 times 10 to the 10th years. Okay? That's not a mistake. That is 68,700 million years. 68,700,000,000 years. That's how long it would take to spend $1 billion an hour. So Avogadro's number, point being here, is an extremely big number, yet that many atoms of a particular element could fit on the end of your fingertip, okay, if you have the right atom. Okay, so now, a mole can be anything, okay, but we are going to deal with moles of atoms, and we're going to deal with molecules of atoms. So this mole is basically a conversion factor, okay, and what we're going to do is we're going to take atoms and we're going to convert them to moles, okay, and to do this, okay, I am going to have a certain number of atoms, and we're just going to set up a T-box. Okay, so we're just going to have a T-box where I have my given number of atoms. Okay, and I'm going to use this as a conversion factor. Okay, so I'm going to have 6 for every, to change it to moles. Okay, on top I will put 1 mole all over 6.022 times 10 to the 23rd atoms. Okay, and that would cancel out my atoms, and that would give me however many moles of something I have. Okay, and you could also use this to convert from moles back to atoms. Okay, and if I'm going to do that, what I would do is I would start with a given number of moles, and I put those in my T-box. And right here, I would use Avogadro's number, okay? But by doing this, now the 1 mole would go on the bottom, and the 6.022 times 10 to the 23rd would go on top. And in this case, moles would now cancel. So I want to see this in your notebooks, this right here. And I want to see this in your notebooks. Okay, so that's how you convert those two things. Okay, now here's an example. I want to know how many atoms are in 3.0 moles of zinc. Okay, so now what I'm doing is I am converting moles to atoms. Okay, and that's where I'm going to use this conversion that I developed here. Okay, this conversion goes from moles, and I'm going to end with atoms. Okay? So I'm going to start with my 3.0 moles of zinc. And I can put any element I want right here. Okay? It doesn't have to be just zinc. I just put zinc. Okay? And I'm going to multiply this by Avogadro's number, 6.022 times 10 to the 23rd. And because I'm talking about atoms, I'm going to put atoms there all over 1 mole. Moles would cancel, and now I would just do the math. Okay, now, to do this math, one of the things you're going to have to do is you are going to have to put Avogadro's number into a calculator. Okay, so here I have a calculator, and what we're going to do is we're going to type in the 3 moles, the 3.0 moles. Okay, so type those in, and we're going to multiply this by Avogadro's number. So you're going to type in 6.022. Okay, now you are not going to use the caret key, you're going to use the exponent key. So you need to find the EE key on the calculator. On this particular calculator, it's second, and then EE. And most calculators will put an E on the screen, and then you type 23. That is your calculator's way of writing times 10 to the 23rd, and then you hit enter. And you get 1.8 times 10 to the 24th. So this comes out to be 1.8 times 10 to the 24th, and now that's atoms. Okay? And it's atoms of zinc is what I should put for my particular unit. Okay, so that is my conversion from moles to atoms. Now, let's say I'm starting with a certain number of moles, or excuse me, a certain number of atoms, and I want to find out how many moles. So now I'm starting with atoms, and I need to convert to moles. You always want to try to plan out what you need to do. So in converting from atoms to moles, okay, I'm going to use Avogadro's number, but now my Avogadro's number needs to be on the bottom, okay, because I'm going to put the atoms down there, okay? So that's kind of your plan that you need to put out. So if I put out 4.55 times 10 to the 23rd atoms of Fe, I'm going to use Avogadro's number to get to moles. I'm looking for moles. They go on top. Avogadro's number goes on the bottom. Okay, and this would be atoms in this case. So the atoms of Fe cancel out. Now you go back to your calculator and you have to type these two big numbers in. Okay, I'm going to do a little clearing here. Okay. So now we're going to type in these two big numbers. Which I forgot what they were. 4.55. Okay. So we're going to type in 4.55. And then we're going to do that second exponent again. And I didn't catch it this time. Second exponent. Oops. Second exponent. Naturally, when I want to do something, it won't work. Let's try this again. We go 4.55 exponent 23 divided by 6.022 exponent 23. Enter. Okay? And we'll use the number that we got, which I forgot to look at, 0.755. So this comes out to be 0.75, and then now this is moles of Fe. Okay, because atoms canceled out. So this is just a conversion. You're converting from atoms to moles, moles to atoms. Now, what's going to happen is we are mostly going to be dealing with chemical compounds. Okay? That's kind of why we did the last chapter. We are now writing formulas. We're not going to be dealing with atoms of any particular element. But when we do this, the math is no different. Okay? Couple terms to remember. I want to see this written in your notes. Molecules refer to covalent bonds. Write that down. Formula units refer to ionic bonds. Write that down. Okay? So all we're going to do is we are going to be, instead of converting moles to atoms, we're going to convert moles to molecules. Or we're going to convert molecules to moles. Or we're going to convert moles to formula units. Or formula units we're going to convert back to moles. The deal is it's all the same math. Okay? Nothing is actually going to change. Because 1 mole can be equal to 6.022 times 10 to the 23rd molecules. Or 1 mole can be equal to 6.022 times 10 to the 23rd formula units. Okay? And molecules and formula units just deal with how things are bonded. Okay? As an example, NH3 is a molecule. As an example, FeSO4 is a formula unit. It all has to do with the type of bond and what they are. Okay? But again, the math doesn't change. So if I'm starting with molecules of something and I want to convert that to moles, okay, I'm still going to use Avogadro's number. So I'm going to start with my given molecules. Okay? And I'm going to use Avogadro's number where I'll put 1 mole all over 6.022 times 10 to the 23rd. And this number will now be molecules. Before, it was atoms. Okay? Remember, you can have a mole of anything, so those will cancel out. So the math is no different. Okay? If I start with moles of something and I want to convert that to formula units, again, the math is no different than what we did already. You're going to have your given number of moles, and you are now going to just multiply by 6.022 times 10 to the 23rd formula units per 1 mole. And the moles would cancel. Okay, so it's no different than what we previously did. So the one thing that's going to be different is I just have to give you the name and you have to come up with the formula. So I want to take 2.8 times 10 to the 24th formula units of potassium chlorate and convert that to moles. One of the first things you should do is come up with the formula of potassium chlorate. So naming and writing formulas will not go away. Chlorate, if you remember, is ClO3. And it's a 1 minus charge. Potassium is K, it's a +1 charge, so this is KClO3. That's potassium chlorate. Okay, so I have formula units that I want to convert to moles. So I have 2.8 times 10 to the 24th formula units. And the big question always comes out, do I have to write out formula units? And the answer is yes. Formula units of KClO3. And what will go on top? I'm looking for moles. 1 mole will go over 6.022 times 10 to the 23rd formula units. So in your work that you have to show for your homework, you will actually have to complete these T boxes. Giving me an answer just won't work. So formula units cancels out. All I'm left with then is moles. And pause the video if you need to work this problem out. And this answer comes out to be 4.65 moles of KClO3. Okay? Look at this problem. Let's convert 3.5 moles of copper 2 iodate to formula units. So now I'm converting moles to formula units. So that's my plan. Okay, how do I get there? Well, I start with my 3.5 moles of copper 2 iodate, and hopefully you know the formula or can write the formula of copper 2 iodate. Okay, and I'm going to put Avogadro's number now on top. 6.022 times 10 to the 23rd formula units. All over 1 mole. The unit mole cancels out. Now do the math. Okay, and again, I could show this with the calculator. Okay. So I'm going to take 3.5 times 6.022 exponent 23rd. and you get 2.1 times 10 to the 24th. So this answer comes out to be 2.1 times 10 to the 24th formula units of CuIO32. Okay? Now, if you've watched the VodCast this far, I will tell you that if you just get rid of that, you can write this and that, and I will be okay with it. Those of you that have stopped watching, you miss out on that. Okay, the last thing that's going to happen in this particular section is you're going to be asked how many total atoms are in a compound. Okay? So, one of the first things you're going to have to be able to do is write the formulas. Again, writing formulas from this point to the end of the year will never go away. So you may as well just keep on top of it, pull out your polyatomic ion sheet, and let's rock and roll. Iron is Fe plus 2. Sulfate, you look up on your polyatomic chart, is SO4 2 minus. And again, sulfate is one that I told you to memorize, so you shouldn't have had to look it up. And I have a plus 2 and a minus 2, so these two just go together as FeSO4. Now, how many total atoms are there? Well, in this compound, there's one atom of Fe, there's one atom of sulfur, and there's 4 atoms of oxygen. So, total, there are 7 atoms per molecule. Bad word, should have said formula unit. Okay, so there are 7 atoms then per formula. Okay, so that's how you count atoms in a compound. Okay, so if I have a compound diphosphorus pentoxide, oh, I can't even count. There should have been 6. Hope you paid attention to that. 1, 2 plus 4 is 6. Oops, sorry about that. Hope you weren't too confused. Because I knew there was going to be 7 in this one. So, diphosphorus pentoxide. Diphosphorus means there are 2 phosphorus. Pentoxide means there's 5 oxygen. Okay, so now my total number is 7 atoms. Sorry for the confusion on the last one. Okay, there really are 6. Okay, and you should be able to take any compound and figure that out. If I have NH4 2SO4, okay, this gets a little tricky, but with this 2, there's 2 nitrogen, 8 hydrogen, 1 sulfur, and 4 oxygen. Let's see if I can do math this time. 2 plus 8 is 10, 11, 4, there's 15 atoms in this one. Okay, and again, that 2 makes it a little tricky. Let me give you another one where we'd have that. If I have let's go CuNO32. Tell me how many total atoms there are in that compound. There's 2 copper? Nope, only 1. But there are 2 nitrogen, and there are 6 oxygens. Because remember, this 2 right here means I have 2 NO3s. So there's my 2 nitrogen and my 6 oxygen. Okay, so why do you need to know that? Because some problems are going to ask you to find the total number of atoms present. Okay, so if I go back to P2O5, where I know that there are 7 atoms per molecule, okay, one of the questions might say, how many atoms are in 2.1 times 10 to the 15th molecules? Okay, And so you would just take 2.1 times 10 to the 15th molecules times this new conversion factor where there are 7 atoms per every 1 P2O5 molecule. Okay, and then you just multiply those two numbers out. And that comes out to be 1.47 times 10 to the 16th atoms. Okay? You should now be able to complete worksheet 1. Okay?